Hi everyone, and welcome to this webinar. The subject of the presentation will be advanced settings for LiDAR survey, drones applications, and it will be presented by my colleague Sam Soliman. The presentation will last approximately 30 minutes, and there'll be 15 minutes set aside at the end to answer any questions you have. If you have a question, feel free to submit it at any time during the presentation. Just use the GoToWebinar window and type your question in and submit it, and we'll go through as many as we can at the end. The presentation is recorded and everyone will be sent a copy after the webinar is finished. So I'll pass you over to Sam now.
Thank you, Kit, and welcome everyone to this webinar. So before we start, I'm just going to mention that I'm expecting some knowledge on your side, having to have some familiarity basically with NAVconfig and some knowledge of the basic concepts of a correct setup and a warm-up of the unit. We will go through the main aspects anyway. So the focus of this webinar is surveying with drones. We will shortly look at the role of the INS, what you expect from it, issues that can prevent you from getting the optimal output from the INS, and the best part of the webinar will be on how to get this optimal output. The INS, it basically provides all the parameters that are required to georeference your survey data, camera shots, LiDAR scans, and so on. So time, first of all, so we can sync all the data to the INS data. That's the GPS time that the INS will use. Position, obviously, either in absolute lat lon alt coordinates or in XYZ local coordinates if you have set a local coord system. Orientation angles, heading picture rule for all the instruments, so for the drone itself, and hence for all your instrumentation. Obviously, having accurate time and position and orientation throughout the data collection is critical, so the INS needs to provide also solidity and integrity of the data. What can prevent you from having an optimal INS output? A wrong or a less than ideal physical setup, we'll see that in a minute, a non-ideal configuration, incorrect initialization, and finally incorrect or insufficient warm-up of the INS. So we will go through each of these and how to get them right. And at the end, I will provide some hopefully other useful information. The physical setup. So first of all, you need to have your antennas properly mounted. That is with suitable ground planes, suitable protection from multipath, and possibly without anything else above the level of antennas. In short, you don't want anything to get in the way of the GNSS signal. EMI, you will have some instrumentations on your drone, likely a LiDAR or perhaps a camera, and these devices can be a source of EMI. So you need to place them as far as possible from the GNSS antennas. A rule of thumb, we say 1 meter. I appreciate that there is a lot of room on a drone, depending on how big the drone is. So you might get away with a shorter distance than 1 meter. That will depend on how strong a source of EMI your LiDAR or your other devices are. Do your best to get them as far as you can from the GNSS antennas. If that shows to be very, very difficult and you cannot keep the LiDAR or any other device 1 meter away from both primary and secondary antennas, if you have to, so to say, sacrifice one antenna, then make that the secondary. Try to protect as much as you can the primary antenna because it's the most important one. So get the primary antenna at least 1 meter, if you can, away from the LiDAR or any other devices. And mind the cables, because if they are not properly insulated, they can be source of EMI as well. And the EMI does disturb the GNSS signal because the GNSS signal is very faint in nature, so it needs to be protected somehow from any interference. Mechanical vibrations, that one of the biggest issue with the drone's installation. So you need to do your best to damp them down mechanically. So at the installation and mounting stage, make sure that the INS is not vibrating too much. High vibrations can be dealt with, we will see in a minute, through appropriate configuration, but they will have a negative impact on accuracy. No matter what you do, in ways of damping down vibrations, you need to make sure that the INS and the LiDAR, or the photo camera, the survey device that are using, are mounted rigidly with no play between them. So it is fine to damp down the vibrations between the INS and, say, the frame of the drone, the rest of the drone, but you don't have to have any damping mechanism or anything else between the INS and the LiDAR itself. Okay, they need to move and vibrate, if they have to vibrate, together, because obviously you will use the INS data to reference the LiDAR data, so they need to have exactly the same kind of motion, no play in between them whatsoever. Another important aspect related to vibrations is that if the arms on which you will have installed the antennas vibrate too much, it means that the lever arm, that's the distance between the antenna and the INS, can change significantly during the flight. And this is not good. You want the lever arm, so the distance between antenna and INS, to stay the same as much as possible, certainly within the tolerance that you have set in your measurements for this distance. So it means that the arms that are holding the antennas needs to be rigid enough so they do not vibrate too much during the flight. If they are very thin, very weak, they will vibrate a lot, and the position of the antenna will change during the flight. So these are the main things for the setup. Now, correct config. Obviously, the two things are related. First of all, a quick one, just in NAVconfig, you can select the kind of applications that you have. So for example, aerial in this case, fixed wing or rotary wing. This is just to simplify NAVconfig settings for you. So you are not presented with a bunch of settings that you are not interested in, that they would be applicable to a land vehicle, for example. And obviously, they have no place on a drone, so you don't waste your time with them. So if you select at the first home page of a NAVconfig, you select your specific application, it gives you just the configuration pages that you are interested in. Okay, configuring the INS basically means putting in the lever arms distance between the IMU and the primary antenna, then the distance between the antenna and the primary antenna and the secondary antenna, and also the orientation of the IMU, how it is mounted in the drone. So the idea is that you need to measure all of this and tighten down the accuracies of these measurements. Tightening down the accuracies means practically that you are removing a lot of uncertainty that the system will have to cope with. So when you say that the antenna is, at a given distance plus minus 10 centimeters, that's more uncertainty than saying that the antenna is at the same distance plus minus 1 centimeter. So by tightening the tolerances, you are helping the system, by reducing the uncertainty. But it is important to get this right. So ideally, you would leave the default tolerance, which is 10 centimeters on lever arms, and run a calibration run, a thorough warm-up. We will go through this in a minute. Then use the improve configuration tool, through which the system will measure, during the warm-up, it will have measured the real distances from the antennas. And through this tool, it will apply this configuration to itself, if that makes sense. So through this calibration run, you leave it to the system to figure out what your real actual lever arms are. This calibration run needs to be completed in RTK or PPK position mode. So either you have corrections in real time, or you can use RINEX files in post-processing to process the calibration run file and extract the optimized configuration from the file. Especially if you are using the same configuration time and again, so you don't move antennas, you don't move the INS on the drone, then doing this is very useful, and I do recommend you do that, because you only have to bother once get your configuration right, then you save it on the system and you use it again and again. Alternatively, if you are confident about the accuracy of your measurements because you have a CAD model for it, for example, like you built a mounting, you know where everything exactly is, how distant things are, so you can tighten your tolerances manually. But always keep in mind that setting a tight tolerance on a wrong measurement is worse than leaving that tolerance loose. You better have some uncertainty rather than having a sure error. So do not tighten the tolerance if you are doing this manually beyond a reasonable certainty. Keep in mind that the system will not refine the distance between the two antennas. That's the 3D distance between the two antennas. So you will have to measure this and accurately and tighten the tolerance to 1 or 2 centimeters. The system will trust you on this. So it's up to you basically to measure the distance between the two antennas. And also another thing that the system cannot figure out on a drone, it can do that on a land vehicle, but not on a drone, is the actual orientation angles between the INS and the drone. So you need to set that. The easiest is to have your mounting in a way that the INS will sit level if the drone is level, and then tighten those orientation angles between the INS and the drone, tighten the tolerances on those angles to 1 or 2 degrees maximum. The default is 5. If you are not sure, again, leave it at 5. The system can cope with that. Just gonna take it longer to figure out. Improve config. This is in the first page of NAVconfig. If you hit that button, it takes you from there, either from a live unit or from a processed file. This is an example of improved configuration. As you can see, the angles have not been refined. What it did though is refining the lever arms. You can see that on the Z lever arm, it had quite a corrections from 45 to 31 centimeters. And if you look at the accuracies, they are down from 20 to 1 centimeter. Also the orientation and the height offset between antennas. So not the distance, but orientation and height offset, they are corrected by the system through the warm-up procedure. If you are doing that manually, tightening the accuracies manually, you do it in the Advanced Tools Accuracies tab of NAVconfig. Mechanical vibration. So as we said, you need to do your best to dampen them down, mechanically, basically. So when you install, when you design your mounting, try to do your best to damp down vibration as much as possible. We can still do a few things to cope with high vibrations. So because we assume that a drone will be operating in good GNSS conditions, because drones will fly over things, so hopefully you will not have a lot of obstructions in the way, we can configure the system basically to trust the GNSS data more than the IMU data. Because the GNSS data is good, open sky, and because the IMU might be suffering from some vibrations, this is what we do. We put more weight on the GNSS. And the way to do this is, one, by setting the GNSS recovery settings to a value of 2. That is basically, imagine the GNSS data and the IMU data disagreeing on, say, the position of the INS. So this value here is how many GNSS updates should take the system to believe the GNSS over the IMU. To give you an idea, the default is 20. So the GNSS will have to keep repeating the same thing 20 times before the system will say, I'm going to believe the GNSS and not believe the IMU. Obviously, that only if they are disagreeing. If they agree, then we are all happy. If they do disagree, you can specify which one the system should be believing more. When you set it to 2, the system will be very quick to believe the GNSS over the IMU. The other thing is that we need to set the vibrations to high, not to normal, but to high. If your vibrations are really bad, You can still set the vibrations to very high, but keep in mind that if you do this, the trust in the IMU data will be limited heavily. So use it with caution. Okay, the system will trust your judgment, and if you are telling it that the IMU data is really bad, this is what very high vibrations would mean, because the noise will be so large that it would be difficult to distinguish between a real acceleration and the vibration. It can still extract sensible data. Obviously, it won't be as accurate as having everything set properly or everything set to, for example, high vibrations. So you can do this, but use it with caution. This is where you would do it in the environment section of NAVconfig. You can set the vibrations level to normal, but on a drone, most of times that won't be the case. High, which is fine. Very high, if you really have a heck of a vibration going on. And this is GNSS recovery. In the advanced tools GNSS recovery section, you can specify the number of position and velocity updates that it will take the system to believe, as I said, the GNSS over the IMU. This is an example of what very, very large vibration can do. In this case, they messed up the initialization of the system, basically. So you can see the trace on the left. That's what happened. On the right, that's the real trajectory of the drone. And that's what we've got by reprocessing the data and setting the vibration settings correctly. So by setting GNSS recovery to 2 and setting vibrations to high instead of normal, that's what they were on the left, we got the data back, basically. We've got the correct data back. So this is to show you how much the configuration of the INS is important. And also what you can do in post-processing. So if your data does look bad, it doesn't mean it's not recoverable. There are things that you still can do. Initialization. So that is about basically getting directions right. Initialization means telling the system which way is forward, which way is up. We have two ways of initializing. That's dynamic and static. Dynamic, that would mean traveling straight and forward. But on a drone, that might be difficult because you will have, for example, crosswind. So you will not be going exactly forward and straight. Whenever possible, use static initializations on drones. If you do that with the correct configuration and setup, meaning you measure the distance between the two antennas accurately, and you tighten the accuracy on that 1 centimeter, then static initialization can be very quick, under a minute, leaving you, time for surveying. If you cannot initialize statically for any reason, or that is difficult, so as a backup option, you can keep dynamic initialization, but which will always be active on our systems. The way you trigger it is by setting a speed threshold that the system will initialize as soon as it crosses that speed. But that speed can be in any direction. So make sure that that threshold is high enough so you do not cross that threshold, accidentally, inadvertently, by maneuvering, for example, the drone, trying to make it take off initially and then positioning the drone in order to initialize by going straight and forward. If your speed threshold is very low, you might initialize whilst doing that, while placing the drone in the right spot for it to initialize. So to avoid that, set the threshold high enough, at least 5 meters per second, 10 meters per second if your drone can go that fast, so that you avoid initializing when you do not intend to. Choose a level spot to initialize. If it is not spot, it's not a problem. Just configure the system. Tell the system that you are not on a not level ground. We'll see how to do this in a minute. The recommended initialization is the static one, as I said, and keep in mind that static initialization requires good GNSS, open sky, because since you are static, the IMU is basically silent. It can't tell the system anything, so you are completely relying on GNSS. So it needs to be good. And one of the things that people, do in these cases is sometimes gathering around the drone whilst it is initializing, but the human body is an obstacle. for a GNSS signal. So you are getting in the way of, usually drones will not be very, very high over the ground. So by standing in front of it, you are getting in the way of the GNSS signal. So try to, leave it alone for a bit, step back a bit, leave the system to initialize. This is where you do it in the environment section. So you can set, enable the static initialization, set the threshold of dynamic in it, specify whether you are level or not. Not level means a slope that is larger than 5 degrees, roughly. And set the environment, which, as mentioned, we are assuming we are in open skies. So in very good GNSS environment. On the left, an example of a garbled initialization where the system has got its directions completely wrong. On the right, again, reprocessing the data by enabling static initialization instead of having dynamic. And you get, as you see, a perfectly neat and sensible trace on the right. The warm-up procedure. So the first thing to say is that you've got a warm-up window of 15 minutes from initialization. That's not from when the system is switched on, that's from when the system initializes. 15 minutes during which the system is in listening mode, so to say. So it's open to learn about the surrounding environment and understand what its real orientation is, how distant antennas really are. So you need to complete the warm-up maneuvers, and we will go through this in a second, within 15 minutes from initialization. After that, the system will be way less open-minded. So obviously on a drone, it will be difficult to complete a long warm-up because of battery life, but on OxTS units that are typically used on drones, that's the XNAV or XOAM 500 or 550, the warm-up can be very quick, under 5 minutes. 5 minutes if you start with a loose configuration. If you start from an already optimized configuration, a tight one, then the warm-up can be under 2 minutes. And if you are post-processing, especially in combined mode, then the warm-up can even be down to 1 minute. Optimized configuration means the one that you get through the calibration run. So the one that you use to optimize your config starting from a loose configuration. During the warm-up, you need to have good GNSS, so open sky spot, and have a varied motion to excite all sensors. So if you are starting from an optimized config, a short warm-up, 2 minutes is enough. If you are doing a calibration run, take your time, do at least 5 minutes, 10 minutes, even better, because remind you that, you need to remember that you will use this configuration time and again. So you only bother once to do this thorough warm-up to improve your configuration. You save it on the system, and from that time on, you just need to do short warm-ups of a couple of minutes. You can monitor in real time the progress of your warm-up through our software. Obviously, you will need a connection to the INS. So either because you have a wireless connection to it, or you can bring the drone down and connect via Ethernet to it, to the INS, and check how the warm-up is progressing if you want it. Otherwise, you can check your data in post-processing. Motion types, as I said, the key is a varied motion to excite all sensors on all 3 axes, gyros and accelerometers. So this is figures of 8, high and low speed, that helps pitch and roll accuracy of the INS. Straight lines will help heading accuracy. Sharp 90 degrees turns in both directions, that will help horizontal position accuracy, and variations of altitude, which should be fairly easy to do with a drone, for vertical position accuracy. Any kind of motion that you can think of that will be part of your survey, that is not included in the above, include it in the warm-up, because you want to prepare the system to cope with that kind of motion. At the end of the warm-up, bring the drone back to the starting point. So if you are doing a calibration run, like I said, 5 to 10 minutes, do a few of each of these maneuvers. If you are doing a shorter warm-up, a couple of minutes, then a couple of each will do, and you are good to go. Finally, some hopefully useful information. A word on datums. This is something that is often important in survey applications. So you have a choice of main datums available with our systems. You can have your output, your position output, your coordinates in one of these main datums, WGS 84, NAD 83 for North America, ATRS 89 for Europe, ITRF 2014. There's a number of them that you can select from if you wanted the output to be in a specific datum. For altitude, we use both ellipsoidal and geoidal models. So geoidal will contain basically an altitude, a difference from the ellipsoidal model, that is undulation. As many of you will know, this undulation is specific to the receiver. It's saved, say, in the memory of the receiver, and it will apply a specific undulation, depending on what part of the Earth it is on, because obviously it has a sort of a grid, and each square in that grid will have its own undulation. So that it depends on the receiver. If you have a better knowledge than the receiver does about the altitude in a specific area, then you can customize this geoidal undulation and type it in. So the system, instead of using whatever comes with the receiver, can use what you instruct it to use. Obviously, because you will still be using a fixed undulation, so a fixed altitude basically above sea level, for all of your survey, the area that you cover in that survey shouldn't be too large, so that the approximation of having the same altitude would make sense. This is where you do it in the Advanced Tools Global Coordinate System tab in NAVconfig. Again, as you see, we have the choice of datum for the output, and then we have either geoid, ellipsoid, or geoid custom. So you would tick this box and type in the offset, the undulation that you want to apply. Another feature that might come handy at times is output displacement. So it means that instead of having all of your output, position, orientation, so on, at the INS location, you can have it at a chosen spot on the drone. For example, at the position of your instrumentation, your LiDAR or your camera, if you wanted. You don't have to do that. The system would work perfectly fine regardless, but sometimes it can come handy. For example, if you are using OxTS georeferencer, which puts together the INS and LiDAR data, there is no need to do that, because you can configure the software with the lever arms between the INS and the LiDAR. But at times, other software might not do that. So if you prefer to have your output directly at the LiDAR location, you can do that. This is where you do it in the Advanced Tools Displaced Output tab in NAVconfig. So all you have to do is basically type in the lever arms, the displacement that you want to apply. Diff corrections. So these are a means to improve the accuracy of your system, the position specifically. There are a number of them. SBAS, to start with, that is free, but it's good to remember that SBAS is only compatible with GPS satellites. So if you had other constellations enabled on your system, we track GLONASS, Beidou, and in the near future we'll have Galileo also enabled on our systems. So if you are using any of these, they can't be used with SBAS. It means the system will not use, it will still track, but not use those satellites in the position solution if you are using SBAS. You can use a field base station, which can give you RTK level of accuracy, but obviously you need to keep in mind that the area that it can cover, it won't be very extended. And also you need to have no obstacles in between, like no obstacles between the base station and the drone, otherwise you will lose your corrections. You can use NTRIP. You will need a good mobile internet connection. The advantage is that they can cover wider areas, but again, if you lose your connection for a while, you will lose your corrections. Most times it can be enough to apply differential corrections just in post-processing through RINEX files. The advantage is that you have no interruptions in the flow, in the stream of corrections. And so you can post-process the data and post-process with RINEX files to improve that accuracy. Regardless of what you do, so of the way you apply corrections in using NTRIP or a field-based station or RINEX, the datum in which diff corrections are applied needs to be specified. The system needs to know about it, because they will come with a datum, and the provider of diff corrections will tell you about what datum that is. In North America, for example, that is highly likely to be NAD 83. But the system needs to be configured, to know the specific datum corrections are coming with, so that it can apply the right transformations. This is where you can select that in the hardware setup page. You can select the format of corrections, enable NTRIP if you had it, enable SBAS if you wanted, and specify the datum of corrections. That is in real time. If you are applying RINEX files, then the datum can be specified through an advanced command that we can tell you about. Finally, just a quick word on post-processing, because it has many advantages. So as we've just seen, you can add diff corrections to improve the accuracy. You can process in combined mode, which will improve your accuracy. I'll show you that in a second. And also, as we've seen a couple of examples of, if you had bad results, and hopefully if you do everything that I've listed above, your data will be good. But if you still have some cases where you have bad results, often it will be possible to recover the data by improving the configuration, by tweaking a few things in the config, enabling or disabling some features. You can have your data back. Very often that will still be possible. The only thing that is not possible to change is the raw data that the system will have logged, so GNSS data and inertial IMU data. Once it is logged, this is it. You can't change the number of satellites that you were tracking. You can't change the level of accelerations that were logged. But what you can change through the config is how the system will interpret this raw data and make sense of it. So combined processing to end with. It puts together the best outcome of forwards and backwards traces. And that will help in improving the accuracy of both position and orientation of your data. One thing that you need to remember, though, is that if you are using the backwards trace for the combined result, the system will have to initialize and warm up from the end, not just from the start. So it will need a correct initialization and warm up right after as well as right before the survey. Okay, this, in return, will shorten the warm-up time. As we said, if you are processing in combined mode, your warm-up time can be 1 minute, down to 1 minute. So in practice, what does it mean? It means that after you are done, basically, with your survey, you need to do a minute or so of straight lines and figures of 8. That is the warm-up for the backwards trace, and then stay stationary on the ground for about a minute at the beginning. That is the static initialization time for the backwards trace. For a backup option, that's dynamic initialization, end your survey with a straight line, which would be what the system would use for its dynamic initialization if needed in the backwards direction. Okay, so keep this in mind if you want. You don't have to process combined, but it does have some benefits. So if you wanted to do that, keep in mind that you can apply this two easy things at the end, so you ensure that you have a backwards trace that is as good as the forwards. The result of this, that's just an example. So same data processed in combined and simulated mode. Top graph, that's the position accuracy. This is with RINEX correction. So we start from a situation, the blue line here, where the system has a position accuracy of slightly more than 1 centimeter, with some peaks up to 3. So it is a good position accuracy, by all means. But if you process combined, you get it down to between 0.5 and 1 centimeter throughout. You can notice the difference. For attitude, the two blue lines, dotted lines, are pitch and roll accuracy. So we are looking at about 0.1 of a degree, and then slowly down to 0.06, 0.05. That's in simulated. If you process combined, you get a solid 0.03, 0.04 accuracy for your pitch and roll. 0.03 degrees of accuracy for pitch and roll by processing in combined mode. Okay, thank you.
Thank you, Sam. So if anyone does have any questions on any of the content Sam covered, then feel free to submit your questions using the GoToWebinar window. And while we're waiting for people to submit some questions, I'd like to quickly draw your attention to the other webinars in our series. So if you go to oxts.com/resources hub, you'll see that we are offering a new series of webinars starting next week on topics like what is included in the next software release and other topics, including how to do an AEB or lane departure warning test. So those are all available to sign up and register at oxts.com/resources hub. We haven't had any questions submitted, so we assume that Sam has done an adequate job in covering all the material, and you have a full understanding of how to use our systems with drones now. And we'll finish up the webinar slightly early. So thank you, Sam, and thanks everyone for joining.
Yeah, thank you everyone. Have a good day.